G'day everyone, welcome to Lubrication Explained. Today I'm going to be talking about synthetic esters with the COO of a company called Biosynthetic Technologies. Now, I've always found esters really fascinating because esters themselves, it's just a functional group, right? It's that C double bond O and then single bond another oxygen. And that's very generic, right? You can have that functional group in an infinite number of different molecules. And so I've always seen esters as being a bit of a technology platform. You can really add whatever kind of functionality you want to an ester, and you can make it very customizable. And I think that there is the great potential that in the future we will see very customizable lubricants where you'll be able to talk to a formulation company and order a very, very specific product for your needs. And I think esters really fit that bill. They also fit the bill because they fit in with sustainability. They can be made from natural ingredients. They can be made carbon neutral or even carbon negative in some cases. And so in many respects, I think that esters could be the future of the lubricants industry. So anyway, I thought the discussion was really good. We got into a lot of technical detail as well as detail about the markets and manufacturing process. I found it fascinating. I hope you do too. Thanks. Hey everyone. Today I've got a really interesting interview. I think predominantly about esters and the idea that esters can be a bit of a sort of a platform for different technologies. So I think it'll be really interesting because obviously esters are very widely used, but personally I think a little misunderstood in the industry. Today we've got Matthew from Biosynthetic Technologies, and he's going to come and talk to us about all things esters. So Matt, do you want to introduce yourself?
Yeah, hi, I'm Matt. Dr. Creek, some of my colleagues call me. We have a running joke about the whole PhD thing, not piled high and deeper. But I am the Chief Operating Officer here at BT and at Biosynthetic Technologies. We're an early stage company that is all around developing sustainable molecules, really for making better futures, innovative solutions. And one of our key technologies is around ester. It's called Estolides, and really excited about the ability to talk to esters and kind of the evolution of that technology with you today.
Yeah, awesome. So let's kind of start with the basics, right? So, esters as a molecule, as a chemical, it's obviously there's the ester functional group,
Mm-hmm.
which, as I understand it, is widely seen in nature. So
Yep.
maybe we could start from there. Like, where would we typically see esters? Where do they come from?
Well, yeah, I mean, esters are one of Mother Nature's great inventions. And so if you've ever cooked in a natural oil, say Crisco type oil you buy on the shelf or peanut oil, you're working with esters. And so really what an ester bond is, it's a carboxylic acid basically connected to a fatty acid. And nature builds these all the time, rapeseed oils, palm oils, castor oils, and you usually have some type of fatty acid. Nature tends to like 18 carbon molecules, and you basically, with an ester bond, you link those to usually a glycerin molecule. Nature likes triols or glycerins, and so you basically have three ester bonds that connect three fatty acids. And Mother Nature has been using this technology for millions and millions of years. We as people interested in, say, lubrication, which is our specialty here at BT in some areas, we have also been using Mother Nature's esters for lubrication. And natural esters have a lot of really interesting properties. They have really good VI. They're biodegradable. They're obviously renewable because they're coming from biosources in nature. We can regrow them and press them. So they've got a lot of really good properties. But it also, to be honest, has some weaknesses. Mother Nature really didn't build molecules for the demanding applications of car engines and gear oil boxes and things like that. And some of those weaknesses in those kind of Mother Nature esters really is around the oxidative stability. So when you get some air or oxygen in these molecules, they can kind of decompose into smaller pieces, and you lose some of that lubricating function. And then the other thing that esters, kind of Achilles heel for this part of the technology, is really around hydrolytic stability. So you get a little water in, and these ester bonds like to kind of fall apart. And what you're left with is kind of a free fatty acid and a glycerol molecule. And once again, you've you've diminished the overall property of that ester, especially as a lubricating chemical. So, but
Mm.
I'd say a lot of positives that Mother Nature has brought to us, kind of with this ester technology.
Yeah, yeah. And so I guess in my head, I've always imagined the ester functional group as kind of looking a little bit like a carboxylic acid, right? So, with the carboxylic acid, you've got the double bond to the oxygen and then a single bond to another oxygen, which is then bonded to a hydrogen.
Yep.
And with an ester, you just kind of throw away the hydrogen and put some kind of alkyl group or some other molecule on the end, right?
Yeah.
So now maybe another question for you is that the traditional way in high school chemistry that we think of, esterification is what it's acid plus alcohol, right? Gives you
Yep.
ester plus water. So
Yeah.
in nature, how is Mother Nature doing that, right? Is she taking alcohols and acids and putting them together?
Yeah, actually, Mother Nature in a lot of ways is more enzymatic. You're using biology to do it, which, to be honest, there's a giant growing body of research called SynBio, where you try to take Mother Nature's essentially enzymatic protein-based approaches for that chemistry and specifically make them better.
Mm.
It's a little different. We as chemists. Have copied Mother Nature, but really not that route. We do more like what you're talking about. Is we tend to take acids, we tend to take essentially free fatty acids in
Mm.
this case, and combine them with some type of alcohol group. And it can be, it could be an OH group on an alcohol, even like methanol. A really good
Mm.
example of kind of the first traditional synthesis of I would say basic man-made esters is really like methyl esters. You take like a C18 oleate, so oleic acid, probably the most prevalently produced fatty acid that Mother Nature produces. And you cleave that off in the glycerols, and then you tend to basically attach like a methanol, or you can do an ethanol. And what's good about that is you can make a much smaller molecule, so it's got much lower viscosity. So you get more solvency, smaller applications. But once again, the big weakness of those types of esters is a really small methanol. That ester bond is big and open and just readily for attack. If you add water back in, you're basically running that reaction the other way. There's
Mm.
not much to stop it from falling apart. And so that's kind of the interesting part of chemistry is, we've kind of a little different than Mother Nature and how we build them synthetically. But because of that, they can go the other way without too much work. And especially if you have any type of acidity present in your molecule. And like most modern lubricants will have some acidity, some total acid number in them. And just a little bit of acidity basically catalyzes that destruction of that bond. And so it's a runaway reaction because the more we break apart, the more free acids we have in those oils. And because there's more free acid, they act as catalysts to further destroy what's rest. And so it's kind of like a runaway reaction once it kicks off, which is why it's a little bit of an issue in some of our lubricants. But
Yeah.
interesting chemistry, absolutely. So
Yeah, right. And I guess just to pick up, so we've talked a little bit about hydrolysis on this channel, and specifically with things like the jet oils, right, which are all polyol esters at this stage.
mhm.
Um, and and one of the discussions that we've had is why you can't really use oxidation as a proxy for the degradation of the lubricant because, well, first of all, with the FTIR, the ester functional group interferes with the signal and all that kind of stuff. But
Mhm.
predominantly, one of the best indications of the breakdown of the lubricant is tan because obviously you get acids as a byproduct of oxidation,
Byproduct.
but you also get it as a byproduct of hydrolysis. So the tan is a pretty good proxy for the overall degradation of an ester.
Yeah,
Yeah.
it's one of the ways we've hydrolytic stability. And we'll talk about this a little bit when we get to Estolides, but it's a big thing for the applications we're trying to tackle with our technology, and it's one of the go-tos is when you're doing hydrolytic testing for life and all that. TAN is really the go-to methodology because it's just clear cut of kind of what's happening as that molecule degrades.
Yeah.
And it was interesting. You talk about like jet oils, like oxidation, and it's funny. Some esters. What I like about esters is you have a lot of freedom to build, like say a polyol ester, like you were talking about. It is you can pick the initiator, right? So I can do like TMP, it's a common initiator, penerythritol, common initiators. It depends on how many OH groups I want to bond those chains onto. And then I got a lot of flexibility in that I guess that R group, as you call it, is how long is it going to be?
Mm.
Is it going to be fully saturated? Is it going to be unsaturated? Is it going to be branched? And that allows a chemist to really tailor things like overall functionality. Allows it to tailor its viscosity. The bigger it can optimize. One thing, if you really want, like we talked in aviation
Mm.
earlier, you need smaller chain fatty acids on those polyols to really get those good pour points. When you start to get to longer chains like C12, 14, 18, which are the chain sizes Mother Nature tends to make, they tend to have pretty average pour points, minus 20 to minus 30 C. If you want minus 50, minus 60, where you need lubricants to operate, say, like in jet engines and in aviation applications, you need much shorter molecules. Valeric acid is a common one, but those tend to be non-bio-based, usually produced synthetically through syngas and other molecules coming out of refining
Mm.
processes. So what's nice about esters is they're very tailorable, and there are things you can do with kind of traditional ester technology if hydrolytic stability is your go-to. And mainly the use of secondary alcohols and branching structure for steric hindrance. But in general, making primary esters like you do with polyesters, there isn't much you can do around hydrolytic stability. And so, when you tend to do these applications, they tend to be in dry applications. You tend to see things run around like toast tests that are dry versus like a wet toast test,
Mm.
because you get a little water in, and we've tested this ourselves, whether it's a monoester, a diester, a polyol ester, a complex ester. Once you start that reaction, it almost self-catalyzes because you're producing more and more of that acid,
Yeah.
and so. But I mean, but oxidative stability can also be an issue for esters. If you're using non-saturated, for example, one way to get really good pour points with using C18s is to use, like, say, oleic acid with that double bond in there. You get a little bit of kink. You get basically, you don't get things overlaying in stacks. You get some branching that helps the pour point overall, but you're going to take a hit to your oxidative stability. So you're going to see that breakdown product in addition to the hydrolytic stability breakdown in those esters as well. So.
Yeah, yeah. So maybe a couple of things to pick up on that you just sort of said there. One of them was, just want to be clear. So one of them you were talking about was the initiator molecule, and you were talking about TMP and a polyol ester. So just for people who are maybe not as familiar, so when you talk about the initiator, that in the acid plus alcohol reaction is the alcohol, right? So there are
Mm-hmm.
a bunch of different alcohols. You've got TMP, which you talked about, but I think most of the jet oils are NPG, right? The neopentyl glycol.
MPGs, I believe some of them use penerythritols.
Right.
You can use things even up like the sorbitol. And,
Yep.
and what you're doing here is you're picking the functionality. So it's the number of those acid groups that I can esterify onto those alcohols. So the
Mm.
more alcohols I have, the more acid groups I can add, right? And
Yeah, and so and that's an interesting one because the way that I understand, let's say polyol esters versus diesters, is that the polyol esters, it's kind of like the alcohol you put in the middle, and then you attach stuff to all the different alcohol groups.
Mhm.
Whereas the diesters, the alcohols are kind of on the outside, right, and the acids in the middle.
Yeah, and usually you use something like sebacic acid, so something that has two carboxylic ends that are
Yes.
tied together in one molecule, and then you're grouping on alcohols on the end of that,
Yeah.
and that's why, like with some diesters or even let's say monoesters, right, where I take a single alcohol like methanol. So if I take methanol and a C18 oleic acid, I'll make methyl oleate, right, and it's one bond. I only have one bond to do that. It's a very hydrolytically unstable. But if I want to improve the hydrolytic stability, I could take something like 2EH, which is another alcohol, but it's branch. It's a branch secondary
Mm.
alcohol. I put that on oleate, and you'll almost double, triple the hydrolytic stability because of steric hindrance. And so the same thing goes for diesters. You can kind of play that game because the carboxylic acid is really already part of the main structure you're adding on to. So
Mm.
you have a little more alcohol group. But when you're trying to make a bigger molecule like a polyol, you pretty much have to put the alcohol group in the center and build the chains off of it, or it kind of doesn't work, if you will, from a chemistry standpoint. So
Yeah. Okay. And then two other things to pick up on, and then I'd like to come back to that hydrolytic stability stuff. So one of the things you talked about was oleic acid and the idea that it has a double bond in it and a kink. And we were talking about how that then affects the pour point, right? So I actually just did a video on the channel about pour point about a week ago. So I guess a couple of things to pick up on there. One thing that you were saying was that as the molecule gets longer and longer, right, that R functional group gets longer and longer, if that's a straight chain, then I guess if you were to zoom out, that molecule is starting to look more and more like a paraffin, right? Overall.
Yep.
So that's why it's negatively affecting your pour point. Then when you talked about introducing the double bond and saying that puts a kink in it, my understanding, geometrically, is that the double bonds are not straight. So rather than having a straight chain alkane, you now have a bend in that paraffin. And that means that the molecules aren't going to stack nicely when it comes to crystallization, right? So that's why that's helping you out with your pour point. But then conversely, the double bond is going to be less oxidatively stable, right? So it's kind of a trade-off.
Yeah, you're a lubrication master engineer here, man.
I'm just trying to. For me, everything is visual, so you have to kind of imagine how these groups look, and then you can kind of put together the physical properties on top of that. So
and so if you think about it, you're right. You're going to get basically what almost looks like paraffinic, like waxing type layering of these molecules that lay on top of each other. And as an example, we built molecules, the same molecule, with and without the double bond. So it's the same molecular weight, using the same starting materials, using the same free fatty acids, and we'll see pour point differences of almost minus 30 Celsius. So that one bond kink can take a molecule's pour point from minus 20 to almost minus 47. And so it's dramatic, that little conformation change where instead of a flat line you're either like this or like this, right? Can have a dramatic effect on pour point. But like most things, it's usually give or take, and so the take in that case is you're using an inexpensive molecule, but you're suffering oxidative stability. Now you can recreate pour points as good using much shorter chains. And the way I think about that is they're not long enough to kind of overlap, and so they almost self kink a little bit because of the shorter length. So
okay, and because I guess once you get shorter chains as well, again, if you zoom out, that molecule now looks less and less paraffinic because the ester functional group starts to dominate the molecule as well, right? And that's got polarity to it, blah, blah.
Yep, polarity, that's, exactly. So
yeah, cool. Now, so a couple of things I do want to touch on. One would obviously be hydrolytic stability, because that's, if you wanted to talk about negative perceptions of esters, hydrolytic stability is definitely one of the main ones. And the other one's probably on the seal swell side. For whatever reason, early on when 100% esters were used as engine oils, I guess it kind of attracted a bit of a negative perception around seal swell. So let's talk about hydrolytic stability first. So again, like you said, it's effectively water interacting with the ester functional group, breaking that down, and it's doing the esterification reaction in reverse, right? So instead of going acid plus alcohol gives you ester plus water, you're adding water to the ester and you're getting acid plus alcohol, right? So that's how I guess I sort of think of it. Now, the way I understand it, specifically with what you guys do at Biosynthetic Technologies, is to use effectively the geometry of the molecule to reduce the chance of that reaction happening. So can you explain exactly how that works?
Yeah, so our technology was I really think one of the key highlights what we tried to do with our what we call an Estolide Estolide technology was really fix that hydrolytic stability part of esters, because we like so many of the other properties. And what we've done is an estolide is a secondary ester. It's not a primary ester would be like what we've been talking about, the polyols, right? You take the alcohol group, you take the acid, you link them together. A secondary ester means you've kind of put it in the middle of something. So instead of these two like in groups coming like that, you're basically making a bond down the middle of something. So in this case, think of a free fatty acid. And you could think of, like, once again, oleic acid would be a perfect example here. So, the oleic acid in the 9-10 position of that molecule usually has a double bond. It can float a little bit, but for the most part, in oleic, it's around 9-10. We'll then take another oleic acid with that head group, that carboxylic acid or that free fatty acid, and we'll basically, our technology allows us to create an ester bond across that double bond. And what we do now is we have what's called an estolide. So it's still an ester bond. We have essentially a catalyst and technology that does that. But now you've basically, instead of having a bond like this, you've got a bond like this. And if you just think about that geometry, it's harder for water to basically get in attack because there's now a steric hindrance along that ester bond. So it's a secondary ester bond. It does not mean, I always want to be clear of this, it's still susceptible to hydrolytic cleavage. But the steric hindrance basically dramatically enhances that property. A good example of this is so we'll make these molecules, and what's nice about this is it's really a polymer reaction. So you'll make one, right, and then now I've got another double bond sitting on this molecule over here, and I come and I stack another one on, and then I stack another one, and it allows us to grow these polymer chains really to any size we want. So we can go small, we can go large. It's another issue that esters sometimes have. We talked a lot about polyol esters, where I pick an initiator like TMP, which has 3 alcohols, or penerythritol. In this case, I just keep growing until I get to the viscosity I want. So I can make very thin and very thick viscosities, but the chemistry stays the same across that entire chain length. And really, hydrolytic stability is never weak across any of those bonds. We've done hydrolytic stability testing. We've done the traditional ASTM methodology to show it, but one of our favorites is we built this. We call this torture test, and we take our material, our estolide. We put in like 1% weight by water. We stir it at like 500 RPM, and we heat it up to 180 degrees Fahrenheit. And then over time, we measure tan, and we see a roughly order of magnitude increase in time until you get similar tan numbers from hydrolytic cleavage. So the steric hindrance really does work, and so it's an interesting molecule in that we're using, once again, kind of the building blocks of Mother Nature to protect the molecule better, and eventually delay the onset of hydrolytic cleavage from water entrainment. It doesn't go away completely, although we're researching technology that eventually may get us there for that as well. And when we get there someday, I could always do a follow-up show with you to talk about it. We have ideas, but it is very intriguing in that it moves the needle. And it moves the needle far enough that in applications where you could never consider an ester for use in kind of water applications, I think you now can. And so we find that, I find that quite intriguing, just using a little bit of steric hindrance to solve one of your problems. So
yeah, that's really interesting. So a couple of things that I noticed there. So first of all, you can basically keep the polymerization reaction running as long as you want, right? So now, I mean, traditionally esters have been thought about as rather low viscosity molecules. Now what we're saying is, with certain reactions, you can make a molecule as big as you want. So now we're talking about potentially having ester base stocks being the foundation for things like gear oils, right? Where traditionally we probably haven't, ester has always been a co-base rather than the main event, if you want to say that. So now that becomes a possibility. The other thing I just wanted to make sure I understand this correctly with the steric hindrance is, let's say, for example, you kind of basically talked about it being almost like a T-junction, right? At a road intersection. So if at the center of that T-junction is the ester functional group, you're using the fact that all of these molecules on the oleic acid?
Yes.
That you've got to imagine they've also got an electron cloud around them, that's kind of basically acting as a blocker to water, right?
Yep.
Um,
Yep.
to use American football terminology. um, just basically, like, literally geometrically getting in the way so that it's harder for a water molecule to get in.
Yeah, and I think it's that, and the fact that if you think about, you're going into the middle of that oleic acid chain, and that oleic acid chain for the most part is a pretty hydrophobic region as well, right? It's
Mm,
a lot of CH groups, not as
mm.
polar itself, and so in some ways you're also you're kind of joining it into, now it makes it a more polar domain once you create the bond, but you're taking kind of that polar in group and putting it next to a relatively hydrophobic group as well. So I think there's some even enhancement that kind of comes from that. But yeah, so you've got it right. You're using the stereochondrics of that bond, and plus the kind of hydrophobic domain, really just kind of trying to create a shell that keeps the water away, makes it harder and takes more energy to get the water into that bond.
Yeah.
So
And do you get advantages over, let's say, something like a polyol ester, as an example, because you are also dispersing the functional groups throughout the molecule? Because it seems like the way that you guys are building it, the you might have many ester functional groups, but they're roughly, in terms of the geometry of the whole molecule, they're roughly evenly dispersed, let's say. Whereas with the polyol ester, all the all the oxygens, right, from the ester functional groups are all centered in the middle. So I imagine
yep.
that the having all the polarity in the molecule right in the middle helps to attract water to it. Um,
Yep.
this is my simplistic
Whereas,
thinking.
and I think that's fair, is whereas in the Estolide, it's evenly dispersed along the entire chain length of the molecule, and that actually it even helps in some other areas, not just around hydrolytic stability. That kind of even polarity, we think, also has really dramatically enhanced the overall solvency of the Estolide molecules.
Yeah, right.
Estolides have some of the lowest aniline points we've ever measured in base oils. So they're just super solvent, and I think that dispersed polarity across the entire entire chain length of that molecule does help in that. So
Okay.
now you actually also asked about seal swell, so I want to make sure
Oh
I don't
yeah, yeah,
forget
yeah.
this.
Let's talk about
And I think it goes back to something you just said earlier: is traditionally esters you think of as smaller, lower viscosity materials, and part of what you see with esters is just because their size, they have the ability to intercalate into these kind of elastomer matrices,
that.
which is what ends up swelling them, right? And in some cases, that is a good thing. I mean, there are people that sell esters as seal swell additives for
Yeah.
base oils that tend to traditionally harden, right?
Mm.
Elastomers, but it has definitely limited their impact on applications. Motor oil, I think you brought up, was a great example. Um, I will say this: our low viscosity Estolide technology looks a lot like esters when it comes to seal swell. They're smaller. It's basically one chain length. It's got similar polarity functions, so it acts a lot like a seal swell agent, and we're aware of that. But what's interesting about our larger molecules, so like we make right now we have essentially an ISO 150 and an ISO 680. So you're talking about like the thickest of the thick gear
Mm.
oils, and those types of Estolide molecules are so big they actually can't get into the elastomer matrix.
Right.
And ironically, what we see is they tend to slightly harden the materials, because once again they have good solvency. They tend to maybe extract some of the plasticizers and other things out of those
Mm.
elastomers, and they'll slightly harden it, more like what you see out of some traditional base oils. So it's a completely different type of ester at that point. So
Right. That's hilarious. So you actually get into a point where you need to add seal swell agents to an ester.
we'll take a little, yeah, well, actually what we'll do is we'll take a little bit of our low viscosity
Oh right.
Estolides
Yeah,
and
yeah. That
dose
makes
them
sense.
in, and you'll get very good, and because of that we've been able to really we have fully formulated gear oils, hydraulic fluids, and motor oils, and we've been able to get through all of our elastomer testing, really because we can kind of tweak those two functionalities. Now, I will say, like, esters traditionally are really, NBRs, HBRs can be kind of challenging for esters, and we have to work on that. But on everything else, we've even passed some of the really challenging seal swell applications for maritime industry, for like
Oh,
stern tube seals and those, and like A Gear Marine being a good example. And so it's another reason why kind of the S-Lite technology helps fix what can be perceived as a problem around seal swell, and we do it by size. There's no real
Mm.
magic here. It's just
Yeah, yeah.
size of the molecule. So
And I just wanted to pick up as well because you guys as a company, I mean, we talked about the potential weaknesses of esters as an engine oil, but you guys have actually made an engine oil, right? Out of the
yes.
Estolides. So, um, first of all, like, how did that project come about? And
I I think what it was is, you kind of spoke this is Esters kind of had a bad rap when it came to engine oil, and in some ways, so we wanted to pick what we thought was one of the more demanding applications where esters had not worked before, as well as show that you could make a biopreferred. We have in the USDA. Biopreferred program here in the United States. If you can get your bio content above a certain ratio, you can claim biopreferred status. So we wanted to see if we could check those boxes. And so we actually started with a fully formulated GFI 5W20, 5W30 motor oil and did the full engine sequence testing on this program. And it was us. We used Estolides and a Group 3 blend, and we passed every engine test first time through, and which was really pretty awesome for a new formulation. We've done fleet trials. We did some work with the Department of Defense. We've got another green fleets, and we did this. My favorite story is we did this taxi cab study out in the Nevada desert, where we had 3 engines run on kind of conventional motor oil and 3 on ours. And after 150,000 miles of desert driving, you take the engines apart. The Estolite engines they were still shiny.
yeah,
And we talked about that solvency, natural detergencies you get with esters. I mean, it kept the engines unbelievably clean, even at drain intervals of like 12,000, whereas kind of the conventional, it's the standard kind of varnish and sludge you pick up with over time. And because of that, we're actually doing we're a small company, early stage. So our goal is not to be an in formulator of engine
mm,
oils, but we want people to use our technology. And so we are trying to right now spin the engine test to get the GF6 formulations on a 0W20, a 5W20, 5W30. And we're working with partners really around re-refined base oils in conjunction with Estolides, because we think the two together have a really nice environmental story
yeah.
for the end user.
So, again, this is just me trying to think through the logic of it. Um, in an engine oil, traditionally detergents and dispersants make up a pretty decent chunk of the ad pack.
Mm-hmm.
With esters having such high solvency for deposits and things like that, are you able to reduce a fair bit of the ad pack by using esters as your sort of core base oil?
I think it's a good thought, and I think the answer is you look at our formulation and the results. I think the answer is yes. Unfortunately, what we did, once again, just because we can't spin too many engine programs, is we took an off the shelf ad pack that was GFI approved, ran the engine test so we could get through, and didn't really get the chance to do a lot of research around how much ad we could pull back.
Mm.
But I mean, the problem was, I mean, here's a good example. We passed every engine test the first time and the numbers look great. It means you're highly over additized at that point, right?
Yeah.
A smart formulator is going to pull that back, save costs, right? For us, it was a demonstration project, so we didn't run all the research. But I think you're spot on with how you could think about smartly formulating an engine oil because of taking advantage of some of those intrinsic properties of the esters. So
Yeah. Okay. Awesome. If we could maybe pivot a little bit just to what goes into an ester, sort of a bit more on the manufacturing side.
Yep.
So I think, one of the things I've seen you guys talk about at Biosynthetic Technologies is the idea that you can have basically carbon negative or carbon neutral lubricant manufacture.
Mm.
I think, again, just perception from the outside is all synthetic lubricants are made in the chemicals industry, and whatever feedstocks you're using, they must start in the petrochemical world. Therefore, in the end, everything is fossil fuel based, right? So like PAOs, for example,
Yep.
At some point they started their life as ethylene gas.
Yep.
So how are esters different? Like, what are the components? If I had to break down the components of esters or estolides specifically, where do they come from?
Yeah, so the vast, I'll say, the vast majority of esters, but not all. Like we were talking about aviation. This isn't true all of them. A lot of them are biosourced. So
Mm.
you take natural oils, palm, castor, soybean. You split them. You create the free fatty acid, which is your acid parts, and then usually you take now uh, a crude or a crude petroleum based derived alcohol for the most part, because if you just use glycerol again, you kind of get the same natural oil, so it's not,
Mm.
and you glue those back together as an ester. And so I would say 80% of the molecule or more is bio-derived, so oleo-sourced from Mother Nature, but not all these. If you're using, once again, low-pore technology, valeric acid, a lot of those can be 100% crude-derived. With our estolides, one of the really interesting things that we do is we have a couple sources that we can use. We can use hydrolytic soybean oil, we can use castor, and if I take castor for example, we're backward integrated with the castor manufacturing sites, and we'll use so the products coming out of castor, we split them, we turn them into very specific free fatty acids that allows us to grow up our estolides to the molecule. But what's interesting is being backwards integrated is on this site that we manufacture in India, is it's very close to the castor crush fields, and so
Mm.
we get the castor oil in. We take the spent crush and mill, and that actually fires our boilers that produces the steam. That's the energy we need to drive our reactions forward. And so we're starting with bio-based materials. We're using steam generated from carbon that's been burned from natural sources. And actually, the vast majority of electricity, not all, but the vast majority is actually generated from a local wind farm in the Gujarat province. And so we're able to actually create, with kind of these specialty molecules, a very low carbon footprint molecule that essentially is for the most part bio-based. Now, to be fair, we have a couple different versions of our estolides. Some are 100% bio-based. Some are maybe 70% bio-based. Occasionally, we use alcohols that are crude derived to enhance certain properties. But for the overall most part is we have a very low carbon footprint in order to do that, and it's a great story. And now we're manufacturing, most of our chemistry is batch esterification. There's a lot of different ways to do esterification. You can kind of build giant continuous plants that are going to just kind of crank out one type of molecule, or a couple that are very specific, so you're not getting contamination. That's good. I mean, we need a lot of esters for certain things, but esters also have a very high degree of specialization, if you will. And
Mm.
there's a lot of companies that do this as well, because it fits well in kind of smaller batch. That means you can have a lot of tailorability on that smaller scale. And that's what I like about our technology, is on this kind of small scale batch, we can really customize this molecule for the needs of the end user. And I told you we can kind of grow them to wherever you need to go. And
Mm.
so if you need a small molecule, medium molecule, a large molecule, we can kind of grow it to your specification. We have a little bit of tailoring we can do on the in groups. We can change the source of the free fatty acid as well. And so we're doing that on a smaller scale. But like I said, and our goal is we like to look at the overall sustainability of what we do. It's one of the reasons we like castor as well. It's grown sustainably. It's not displacing other food crops. It's well integrated in kind of one geographic, so you're not moving it all over. So by the time it leaves the gate in India, we really only have to move it one more time to kind of our end user application. So
Yeah.
yeah, so
And I guess
it's a fun
there's
technology.
Yeah, I
So
mean, castor oil's got a pretty long history in the lubricating world, right? I mean, just
yeah,
the trivia is obviously castor oil, castrol. That's where
yep,
the name castrol comes from, right? So
absolutely. So
yeah, um, yeah, okay. So I mean, I was going to ask the question about the kind of ester, let's say, business landscape, right? Because like you said, you do have some of the bigger players cranking out uh, maybe what you would describe as being commodity esters,
mhm.
right? So you've got a menu of 6 different kinds of ester, in those viscosity grades, and if that's not going to work for you, then kind of tough. Versus what you guys do, which is a little bit more tailoring, and to me that's what the interest is in esters, because I guess we're going to title this Esters as a technology platform. it really does feel like with esters you can sort of build out the molecule you want. It's almost like having a bunch of Lego bricks and saying, I want to make make my own thing, right, rather than what's on the box. So
Yeah, exactly. And
yeah,
and that's some of the fun. If you give chemists the ability to tinker, like we do with Estolides, just where we get excited. And
yeah,
a lot of respect for people that can produce commodity products every day in and out in spec on massive scale. I mean, don't get me wrong, there's a need for that for
yeah,
applications, but there's also a need for these kind of specialty applications. What's nice too about our technology is this is one of the things that most customers are going to ask is, we talk about specialization and more niche, but can you scale? Because a lot of times,
mm,
if I really want to have an impact on the overall sustainability of our world, you have to be able to scale your technology in some capacity. And so far, the Estolide technology has proved very scalable, and we have a couple different ways we can tackle that. We've studied ways of actually building continuous plants that can make specific types of Estolides using hydrolytic soy oil and, say, lauric acid. And we've looked at castor. And so we've got a couple of ways of getting there. And if you think about it, that's important because in different regions of the world, not everybody's on the same technology. Castor, for example, is almost primarily grown in India. Like
mm,
90% of the molecules grown in India. But if I want to produce Estolides here in the United States, I would probably want to use local sources of fatty acids, so local oil. And in that case, soy oil and hydrolytic oil is by far the predominant choice for making Estolides. If I'm in Malaysia or others, sustainable palm is probably something I'm thinking about, or in China, access to sustainable palm is better. And so part of it is being able to adapt your technology to the feedstocks where they are, where you are in the world. So
yeah. It's so cool. I mean, one of my sort of interest areas is what does the state of the lubricant industry look like in 100 years when we are in a post fossil fuels world?
yeah,
Without crude oil, you're still going to need lubricant, right? So what are we going to
yep.
do? And esters seems like it's well suited to being one of the core technologies of the future. I'm like reading about the ionic fluids and all that kind of stuff, but I guess one of the advantages of esters is it sort of fits in with our existing technology and supply chains, right? So the cutover, if we ever needed to cut over from mineral oils to esters, that's a relatively easy change to make. Whereas with something like ionic fluids, although they're very cool, we're so far behind on the research side and like you said, scaling the technology as well. We don't have the manufacturing facilities to sort of really be able to do that, I guess.
Yeah, it's funny. My buddy in graduate school in the same group, he started some of the early ionic liquid research, and I remember what it took just for him to make a couple grams of the stuff. But that's once again, you hit it. It's why I like Estolides is we basically drop into existing plant technology. You don't have to go buy some new piece of equipment. You don't need some new magic catalyst. You don't need some new technology to come out of nowhere. We can literally do it in plants that already exist, and that really helps from a manufacturing. Because you're right. 100 years from now, as we change over, if we have to rebuild everything, it doesn't make sense. And so finding things that fit, like Estolides, I think makes a lot of sense. So
On the application side, when customers come to you, do they request specific properties? Like how does that relationship happen? Is it more like they've seen your existing product line and then they choose something from the menu, or being that you guys are a sort of a small batch customizer of molecules, do they say, hey, I would like my ester to do X, Y, and Z. Can you build me a molecule that does it?
I'd say the majority of our customers, they've probably seen our product literature. We've put together a number of what I call prototype formulations: gear oils, hydraulics, motor oils, and we're honest. We have the data and we have the exact formulations we've done. We've done blends with PAO. We've done blends with group 3s and group 2s and group 1s at different viscosities. And because most customers, I mean, we're realistic. Most people don't want to come in and do 100% drop-in replacement. It's usually a blend or some way of making the product, more tailored. So most are really kind of seeing that literature and take it. What we do see is we serve more than just the lubricant market. We're in metalworking, we're in
Mm,
personal care, and we'll see that we'll come in and say, I like this, but if I could have X, I could launch this whole new product line. And we actually, we've just brought it online. We built a new Estolide molecule specifically around that custom request. I will say the only caveat on that is the global registry to pass the global regulatory process now for all the countries. If you want to launch a global project, it's quite expensive and quite complicated to register your molecule in all these different markets now. And as a small company, we always have to, early stage, we have to think about how we're using our resources. And so, we want to have kind of this core technology that we get out there. So it's not unlimited customization. We try to work in the framework of what regulatory we can change with the molecules that we've registered. But it was something that I didn't appreciate when I first started developing this chemistry, is just how much work there now is when you're building a brand new molecule from scratch on, proving to the regulatory bodies of really all the countries, is it safe? Is it effective? And so it's something to consider when you're developing new molecules and new formulations as well. And so a different angle to think about. And so like if you're thinking about what molecules am I going to choose, what different N groups, you want to use things that have kind of been used before or known that you can get some read across to help speed that process through. So,
yeah, awesome. Hey, I guess I should call you Dr. Matt. Thanks. I thought that was fascinating, and we kind of you definitely answered all my questions. I think esters is such a fascinating part of the business because of the customization, right? I mean, people talk about esters as being a single group, and within the API groups they get lumped in with everything else, right? With PAGs and PIOs and everything like that. But yeah, the customization I think is a really kind of growing part. Maybe one final question before you go would be,
sure.
Where do you see the ester market in, let's say, 10, 20 years?
I think I see it growing. We've seen kind of green waves, if you will, in the past, and green fluids. And right now there seems to be a pretty significant groundswell around sustainability. And you see this, companies now have sustainability officers. It's part of their, investment banks are looking at the sustainability when they make investments now. And so in a lot of ways, we're baking sustainability into the things we do. And what I find interesting is a lot of companies will go and they do all the easy stuff to make themselves sustainable, right? I put in LED lights. I more fuel efficient fleet, and then you kind of get stuck and you think about, well, what's the next tier of things I can do? And that's why I like things like Estolides and Esters as well. If I'm running manufacturing plants that's using lots of metalworking fluids or hydraulic fluids that have to be replenished on a regular basis, that are all derived from petrochemical carbon. Well, if I want to become more sustainable, I can change that out even with blends to bio-based products. And so I think in order to hit our sustainability targets and drive it forward, we're going to move more towards these bio or renewable sources of carbon. So things like esters are just going to have to play a role in helping us achieve those objectives. Now, realistically, if you look at the carbon balance of the amount of carbon from petroleum that goes into a lubricant versus a fuel, it's still a pretty small cut, right? Just to be honest, I think 99.9% probably goes into fuels, and the small leftovers is really in the lubrication world. But that doesn't mean we can't make an impact here. And so I think you're going to see it with fuels. You've seen this a lot with fuels. A lot of syn fuels now are going this way, renewable diesels and et cetera. And I think the industry is pushing this way with lubricants. And I think as we continue to enhance the performance of esters, it's not just a renewability or a sustainability claim that you're making. It's a performance claim that you can make. And there's always a willingness to pay for performance if it fits your application. So,
yeah, that's interesting. And I mean, one of the things we talked about at a summit a couple of weeks ago was the idea of customization of lubricants, and end users, right? Like if I have a gearbox and I need a very specific performance rating out of that gearbox, the idea that maybe in the future I'll be able to like request a very, very specific lubricant, and you can kind of only really get that from Esters and a couple of other platforms. So
Yeah.
yeah, I think personally, I think the future is bright, but we'll have to see how it plays out. Yeah, cool. Hey, Dr. Matt, thank you so much for talking to us today. Really appreciate it. Obviously, all the knowledge that you brought. I think we hit so many different areas of where you can customize esters. And so I think hopefully everyone really enjoyed the discussion. As usual, if you've got questions or comments, leave them down below, and I'll see if I can get to them. But thank you.
Thank you for the opportunity. It's been a lot of fun talking about it.